Hello everyone, welcome to File-Based or Digital Moving Media Workflow Part 1. Allow me to extend a warm welcome to you. Let me briefly introduce myself. My name is Hoseyn Omid. I work at IRIB, Audio and Video Department. Today I am here to talk to you about a little part of file-based moving media workflow. I'd like to give you a brief breakdown of it. The purpose of this presentation and my objective now is acquisition of basic knowledge and understanding of some concepts and terms in file-based moving media workflow. My presentation and talk are divided into 6 parts. I'll start with introduction. Then I will talk about transition of traditional tape and increasing use of disk drive. Next, type of storage, MAM and metadata, playout, and finally studio automation and conclusion. I think everybody has heard about videotape. As you all are aware that film was and remains one of the most notable forms of storing visual information either as a single static format, as in a photograph, or a series of discrete images on a continuous linear medium, as in a motion picture film. For at least the past 3 decades, moving images and sound recordings have been stored on various media including wires, plastics and vinyl materials, rigid metallics, or other polymers, but primarily these recordings have been captured on the most well-known magnetic media, simply referred to as tape. In 1980s and 1990s saw a continual progression of advancements in videotape recording formats. Disk storage technologies were barely infants during the development of a maturing digital videotape era. Manufacturers continued to add new products that used the emerging compression technologies and placed them into linear tape formats, knowing that eventually the deployment of disk-based storage, production, and editing was on the horizon and would ultimately be the replacement storage medium for those formats they created. Once the disk or disk, the former being the optical form, the latter being the magnetic form, became the formidable solution that it is today, the recording processes began to move away from linear tape and onto solid-state media, removable disk media, and transportable, removable hard disk media. With mobile and wireless technologies where they are today, many have not even a clue about what recording a video to a VHS tape is. To this generation there are no moving parts, just screens and the ether. This is where we are headed, any image, anywhere, anytime. Yet, managing that data becomes the $64 million question both technically and virtually. This is where this presentation helps the user and the technologist to better understand how the pieces fit together into a cohesive workspace that functions in a productive and efficient manner. Storage technologies have fundamentally changed the landscape of digital media in a profound way. Gone are the days of using a single hard disk drive on a workstation as the sole means to store digital content. Let me use a table at next slide to explain history of recording and media. This table shows selected history of recording and physical media developments. Digital video recording is a generalization and terminology that has come to mean anything that is not expressly an analog recording. These much belabored references have worked their way into every facet of the industry, compounded even more by the widespread introduction of high definition and the transition from analog over-the-air transmission to digital terrestrial television or DTT broadcasting. The developments in digital media recording took several steps and paths to get to where it is today. The formats that are commonplace today evolved through a combination of various moving media technologies, extraordinary improvements in computing capabilities, and adjustments to production and information technology workflow, as well as a gradual industry acceptance. To sum up, these are core technologies for digital disc recording: spinning magnetic disks, digital image compression, networked services. The third core technology, the development of the spinning magnetic disk drive and ultimately disk arrays, would be paramount to the success of digital video recording and storage. Although digital linear tape for professional video recording was available before disk drives of comparable storage capacities, the disk drive made possible nonlinear storage and retrieval, the emerging technology that promoted the successful development of digital media overall. The spinning disk would, and still today, prove essential to the development of modern compressed and digital video recording, even though there have been great successes with optical disc platforms, solid-state and flash memory, and even to a lesser degree, holographic recording. The hard disk drive still remains the predominant storage media for moving images. With that said, The early development of compressed digital images was governed by the storage capacity of the hard disk and by the processing technologies available during these early times. Much like the software that didn't enter into widespread usage until the code could be stored reliably and efficiently, media would remain on videotape for many years while technology developed and market usage grew. The technology that leads to the success of digital media recording and storage development began with those standards developed out of the Joint Photographic Experts Group JPEG, who, in 1992, standardized the toolkit of image processing based on a lossy compression format used in the capture and storage of photographic images. The JPEG standard specifies how an image is compressed into a stream of bytes and subsequently decompressed back into an image. The JPEG standard specifies only the codec and not the file format used to contain the stream. Following the JPEG lossy standards development, the committee later revisited the lossless coding mode within JPEG. The JPEG LS mode was a late addition to the standard, and in the baseline form of JPEG not using arithmetic coding, the algorithm used was not a state-of-the-art technique. However, this eventually led to the discussions from which came the JPEG 2000 standard prominently used today. Video applications eventually begin to use a new compression format designed for moving image applications. MPEG would be that new compression format. The standards process began with the formation of a subcommittee in the International Standards Organization ISO, which would be called the Moving Pictures Experts Group MPEG. The first meeting was held in May 1988 and was attended by 25 participants. The first MPEG-1 codec would be built on H461. The ITUT video coding standard, originally designed in 1990 for the transmission of video and audio over ISDN lines. For more information, look at slides background picture and refer to https://www.mpeg.org. Network services is the third core technology, along with many other systems, digital video technologies, storage systems, and their interfaces tend to depend on the principle and structures of networked systems. The components of networking contribute to real-time and non-real-time operating systems, file export and interchange, and content management or distribution. Most of the data-based networking technologies developed for data-centric and computer systems are applied in the structure and feature sets found in today's video servers, their storage subsystems, and the intelligent management of media and associated metadata. The components of networking contribute to real-time and non-real-time operating systems, file transport and interchange, and content management or distribution. Most of the data-based networking technologies developed for data-centric and computer systems are applied in the structure and feature sets found in today's video servers, their storage subsystems, and the intelligent management of media and associated metadata. Networked services are the key to workflow collaboration, to high-speed interconnects, to content delivery mechanisms, and to the internal architectures of secured and protected data storage systems. Even as the world evolves through the 1 and 2 gigabits Ethernet topologies, to the 4, 8, 16 and 32 gigabits fiber channel systems, and on toward 10, 40 and 100 gigabits technologies, media storage infrastructures will keep pace with these developments in order to support the continually growing demands on video, audio, and data. Okay, let's summarize briefly what we have looked at. A brief look at the history of video storing, digital video recording overview, an overview of the main reasons for the development of digital disc recording. I'd now like to move on to the next part, storage technologies. I think everybody has information about storage media, such as SSD, HDD and its form factor 2.5 and 3.5 inches, and other sizes, and enough your knowledge about the types of transmission lines and ports and types of storage media including SATA, SAS and NLSAS. We begin this section with centralized disk array storage. In this part, you will learn the basics of storage arrays. We're going to start by looking at what a storage array is, and then we will look at the key components of the storage array, and these are controller enclosure, drives and drive enclosure. Next, we will take a look at the enclosure addressing scheme, and then we will look at what a SCSI enclosure service or says. After looking at the components of the storage array, we will see how these components work together. We will then look at the benefits of storage arrays. We will also look at what a direct attached storage or DAS is, and then we will look at the advantage of the storage arrays over the direct attached storage. Next, we will look at the types of storage arrays, and these are network attached storage or NAS array, next storage area network or SAN array, and finally unified array. When we cover NAS array, we will touch upon the file-based protocols such as NFS and SMB SIFTs that are used by the NAS arrays to communicate with the host computers, and then we will look at what a storage network is. When we cover the storage network, we will also touch on block-based protocol. Lastly, when we cover the SAN array, we will also look at what lengths and volumes are. Now, let's begin with the storage array. So, what is a storage array? A storage array is a storage system that provides data storage to the computers connected to it through a shared network. Storage arrays come in various sizes, from the ones that can be kept on our computer table to the ones that are extremely huge and need to be kept in data centers. Let's look at the physical components of a storage array. The typical components of a storage array are controller, enclosure, drives, and drive enclosure. A controller is a printed circuit board that contains a processor, memory modules, and firmware. It is often called a head or storage processor or a node. The controller acts like a specialized computer that manages all the functions of a storage array, including I/O operations, data recovery in the event of disk failures, and management of disk capacity. A controller enclosure is an enclosure that contains one or more controllers, power supply units, fans, and other miscellaneous components. A drive enclosure is an enclosure that contains an enclosure controller, monitoring card, multiple drives, power supply units, fans, and other supporting components. The drives in the drive enclosure are hot swappable. This means that we can unplug a drive when it fails and then plug in a new drive. Now we will talk about the enclosure addressing scheme and SCSI enclosure service that is implemented in the drive enclosure. The enclosure addressing scheme is used to identify the devices in the drive enclosure by assigning each and every device a unique address. Each hard disk drive is assigned an address based on its location in the drive enclosure. The enclosure addressing is important for troubleshooting and parts replacements. The SCSI enclosure service, or SES, is a technology that provides the means to monitor and manage the health of the drive enclosure and its components. SES can be used to detect and manage the state of power supplies, fans, drives, displays, indicators, and locks. For example, we can have a threshold limit on the power supply's voltage, and if the 12-volt output of power supply varies by plus or minus 5%, then an alert can be sent to the administrator. The SCSI enclosure service is either implemented on the enclosure controller or on the monitoring card that is installed in the drive enclosure. Now let's see how these components work. In the diagram we have a controller. It has a processor, usually an Intel processor, and memory modules. The ports on the controller that connect to the storage network are called front-end ports, and front-end ports doesn't necessarily mean they are on the front side of the storage array. The storage array receives the incoming read-write requests from the host computers through these front-end ports. The storage controller's processor, with the intelligence provided by the firmware, processes these requests for internal action. The controller also uses high-performance memory modules called RAM or cache, retains the data until it is written to the hard disk, and it is also known as cache. RAM memory loses the data when there is a power, whilst the data in the DRAM is protected through battery-backed power in the event of an unexpected power failure. The DRAM cache accelerates the performances of the storage array through read cache and write back cache technologies. Read cache is implemented by keeping the frequently accessed data in cache, so that a read request from a host computer for frequently accessed data can be served immediately without accessing the disks all the time, and write back cache technology whenever an incoming write from the host computer reaches the cache. An acknowledgement to the host computer without waiting for the data to be written to the hard disk. Both read cache and write back cache increases the responsiveness of the input-output operations, which otherwise would have been slower because of the mechanical nature of the hard disk drives. The backend of the controller consists of ports that connect to the dual-ported hard disk drives tray through their interfaces such as SATA, SAS, and fiber channel. The connections to the dual-ported hard drive are in active passive mode, which means that only one port of the hard disk drive's two ports is active at a time. The major benefits of using storage arrays are high availability, increased capacity utilization, and increased performance. Storage arrays provide high availability by providing more than one of the same components such as drives, controllers, power supplies, and fans. Storage arrays increase the capacity utilization by efficiently managing the allocation of storage resources. Let's find out what happens in the absence of a storage array. Since of a storage array, each server has to depend on its own storage, which is usually one or more hard disk drives directly attached to it, and such storage cannot be shared with other servers. This direct attachment of the storage to a single server, either internally or externally, is called direct attached storage, or DAS. The disadvantage of direct attached storage is that while one server may have plenty of free storage capacity available, another server may be running out of space, and there is no option to share the free capacity available in one of the servers. Storage array addresses this problem by having storage as a single pool that can be shared among the servers. As a result of direct attached storage, the overall capacity utilization is less. The solution is to ensure that storage is no longer attached to individual servers, but rather belongs to a storage array which has a single pool of storage. Now let's discuss the types of storage arrays. There are three types of storage arrays: network attached storage, or NAS, a storage area network or SAN array, unified NAS and SAN array. Let's begin with the network attached storage. NAS is a storage array that connects two host computers through an IP network and communicates with them using file-based protocols such as NFS and SMB, CIFS. Let's understand a little bit more about NFS and SMB CIFS. NFS stands for Network File System. SMB stands for Server Message Block. It is Microsoft's protocol for the Windows file system that allows file sharing over a network using a client-server model. CIFS stands for Common Internet File System. It is a public version of SMB. In short, NFS is for the Unix or Linux-based operating system, whereas SMB, CIFS, for the Windows operating system. Most NAS storage arrays support both NFS and SMB CIFS, but for the sake of arguments, let's say the NAS storage arrays support only SMB, CIFS, then the Unix or Linux-based host computers can access NAS storage arrays using the Samba client. Samba is an SMB, CIFS file server that runs in a Unix or Linux-based operating system. Alternatively, if the NAS storage arrays support only NFS, then the Windows operating system can access NAS storage arrays using the NFS client. Before we define the SAN storage array, let's explain what a storage network is. A storage network is a network that was developed for transporting block-based protocols. The block-based protocol is a protocol that transports an entire block of data. On the other hand, the file-based protocol transports only one byte of data at a time, and it relies on the lower-level block protocol to reorder the bytes into blocks. Object-level storage and storage network is a network developed for transporting block-based protocols. Object storage, the ideal is for relatively low performance storage at a relatively low cost. That is designed to serve the needs of the internet workload and so by internet workloads. The concept in object storage is that you have an object right now. That object can be any kind of file. There aren't really any file restrictions or anything like that. There are some characteristics that are very important, but as a general rule, any kind of file can be an object, so we'll throw a little object in there now. There are 4 essential components to that object that make it usable in the computing sense, right? The first one is for every object we have to have an ID. We have to have some sort of a unique identifier that lets us know that what this object is. When it comes time to retrieve it, that's the first piece. The second piece is obviously you've got to have some data. You know what's the point of having a file and all of this information about it if you don't have the data itself. So this could be an Excel file, it could be a video file, it could be an audio file, any kind of file. But you've got to have the actual data itself. The third piece that you have to have is metadata. So what is metadata? Metadata is everything that you need to know about this file and about the data itself. Who created it? When was it created? What is it used for? What is the file type? How large is it? And metadata is what makes it possible to go out and find it, search it, index it, so that you can bring it up and use it whenever you need to. Because again, all that's being displayed outright now is the ID. The ID is not terribly useful. And then the last thing that you have to have are your attributes. Now attributes are related to metadata. They aren't exactly the same thing, but they're close. Attributes can be, are certain users allowed to override it, are certain users allowed to download it, are certain users allowed to delete it. So the attributes are about the object itself rather than about the data.
Hi guys, welcome to OpenIO Storage Story. I am Enrico Signoretti, and in this video I want to talk about the different types of storage and compare their main characteristics to understand better the use cases and the kind of application they are best suited for. Let's start with the block storage. This kind of storage system is usually located close to the server, in the same data center, and it organizes data in separate volumes accessed by one or very few servers simultaneously. The volumes have the layout of local hard disks, presented in the form of sectors and tracks. Most common access protocols are FC and iSCSI, and all of the communication happens on a dedicated storage area network based on lossless Ethernet or FC equipment. This type of storage is very good for databases and virtual machines, and more in general for all those workloads that require low latency and high IOPS. Unfortunately, block storage systems are also characterized by a very high cost per gigabyte, and most of the implementation in the market still rely on scale-up dual controller designs, with a total capacity that can hardly reach the petabyte level, while maintaining a good performance consistency. The limited scalability drives up complexity and costs in large capacity scenarios. In the last few years, all-flash arrays have become more common, and now they account for a good part of primary storage sales. Flash memory is still 10 times more expensive than hard drives though. But again, the goal remains absolute performance here, and thanks to its very high speed and the kind of data stored in this system, it is possible to implement advanced techniques to reduce the data footprint, including data duplication and compression, alongside snapshot and theme provisioning, mechanisms which are of help in reducing the cost to a reasonable level. The second option is file-based storage, or NAS. This type of storage system is connected to the local area network, accessed by servers as well as other types of clients such as PC. Data is organized in a hierarchy of files and directories, shared through protocols like SMB and NFS. Because of the additional file system and the network layers, performance features are not as consistent as for block storage, but this kind of storage system can easily reach very high throughput, making them good for a large set of use cases and all non-latency driven workloads, where scalability is not the key. In fact, most of the systems available in the market are still scale-up, and only few of them show scale-out capabilities due to architecture limitation and the file systems. The dollar per gigabyte of NAS systems is usually lower than block devices, also because they are often configured in an hybrid configuration. A limited amount of flash memory is aimed at serving frequently accessed data and metadata quickly, backed by a large pool of hard disks. Caching mechanisms and automated tiering functionalities are in charge of data movements between different storage tiers. Multi-petabyte installations are now more common than in the past, but the cost of these systems is still high and they can become complex to manage when capacity increases. Object storage is a totally different story. This kind of storage is designed to offer the best accessibility and reliability at scale, making it possible to connect any type of device from anywhere from any sort of network connection, which can support protocols like HTTP. Depending on the implementation, also access parallelization becomes a key characteristic, allowing millions of devices to access the same information simultaneously. It is not a case that sometimes object storage is referred as the storage backbone of the cloud. Data is stored in the form of an object, which is made of data itself, usually standard file, associated with rich metadata fields and unique key. Contrary to what happens in file system hierarchy, objects are stored in a flat namespace and can be retrieved by searching metadata or knowing the key. This is also why object storage is considered a very good option for storing large sets of unstructured data. The most common protocol to access an object store is S3, which is also the name of a public cloud service provided by Amazon AWS. Even though S3 is not as common as file or block interfaces, the number of solutions supporting it is increasing by the day, providing a seamless access to the object store for legacy applications, by adding a gateway, for example, or directly from the application themselves. Because of its scale-out nature, the access protocol involved and potential network issues between the storage system and the device accessing data, latency is not consistent at all, but throughput could be massive. Many modern object stores have strong multi-tenant capabilities, enabling end users to consolidate several types of data and workloads in a single system. This helps to simplify and drive down the TCO of the entire infrastructure. Common object storage implementation shows similar characteristics and very high scalability when compared to block and file storage. The $ per gigabyte figure is also very low, and multi-petabyte installations are pretty common. These systems are scaled out, with each single node in the cluster taking care of a certain amount of capacity. Flash memory is used for storing metadata only, and hybrid or flash configuration are very rare and aimed at solving very specific use cases. Traditional data footprint reduction techniques like deduplication or compression are not really applicable here, mostly because it is more and more common that unstructured data already comes in compressed and encrypted formats. On the other hand, erasure coding or more recently distributed erasure coding techniques improve overall efficiency and durability when data chunks are dispersed in several nodes or locations.
When talking about the SAN storage array, it is important to mention how the storage is presented to the host computers. The storage capacity of a SAN storage array has to be shared among the host computers, so it is divided into logical disks that are assigned to the hosts. These logical disks appear to the hosts as local disks. The logical disks, or logical units as they are usually called, are identified by a unique number called the logical unit number, or LUNs, play a vital role in the management of storage. In the SAN storage array, they provide a logical abstraction between the host computers and the hard disk drives of the storage array. The terms LUNs and volumes should not be confused with each other, while a LUN is a unique number that is assigned to a logical unit. Volume, on the other hand, is a broad term that denotes a contiguous area on a storage device and includes LUNs and partitions. Now, let's look at the unified storage array. A unified storage array is a storage array that supports both file-based protocols and block-based protocols. Host computers can access the unified storage arrays, either using file-based protocols or using block-based protocols. They are also called multi-protocol storage arrays, and that brings data protection is the process of safeguarding important information from corruption, compromise, or loss. The importance of data protection increases as the amount of data created and stored continues to grow at unprecedented rates. When looking at data protection, many factors need to be considered. RAID, EC, and replication are three ways for data protection in storage systems. RAID stands for Redundant Array of Independent Disks. and combines multiple hard drives together in order to improve efficiency, depending on how your RAID is configured. It can increase your computer's speed while giving you a single drive with a huge capacity and increased reliability. RAID works by placing data on multiple disks and allowing I/O operations to overlap in a balanced way, improving performance. Because using multiple disks increases the mean time between failures, storing data redundantly also increases fault tolerance.
RAID 0 combines multiple disks together into a single logical drive. RAID 0 is also called a stripe set or a striped volume. Data is written by striping across all the disks in the RAID set. RAID 0 provides us with two benefits. It increases performance, and it has the ability to create large logical volumes out of many smaller disks. However, RAID 0 does not provide any type of data redundancy, and thus a failure of one disk can make entire stripes of data unreadable. RAID 1 is the simplest way to secure data, and it does this by mirroring disks. Most servers use RAID 1 to mirror two boot drives and thus protect the operating system. But then how does RAID 1 survive disk failures? Well, RAID 1 can survive a single disk failure, and it can even survive multiple disk failures, but it cannot survive the failure of two mirrored disks. RAID 5 and RAID 6 are mostly the same, in that they use a parity drive to protect multiple data drives. If you understand how one works, then you'll get them both. As with RAID 0, RAID 5 stripes data across a large number of disk drives, but it also writes a parity checksum on another drive. The parity checksum is used to protect the stripe of data from disk and media failures. RAID 6 differs only in its use of two parity drives. If a disk fails, then the missing data can be mathematically reconstructed using the surviving disks and the parity checksums. And with two parity checksums, RAID 6 provides a higher level of durability, one that can survive two disk failures. With RAID 5 and RAID 6, we achieve two storage goals. Parity gives us protection from hardware failures, and data striping provides performance. Once you understand the basic RAID constructs, then you can understand hybrid RAID. The most common hybrid RAID combines mirroring, RAID 1, with striping, RAID 0, to give us RAID 0 plus 1 and RAID 1 plus 0. RAID 0 plus 1 adds mirroring to a striped volume. It takes one RAID 0 volume and mirrors it to another RAID 0 volume. Data that is written to one RAID 0 volume is mirrored to the other RAID 0 volume. And RAID 1 plus 0 stripes data across mirrored volumes. Both of these give us the benefits of RAID 0, which is performance, and RAID 1, which is protection from disk failures. And it doesn't end there. There are other advanced RAID models like RAID 5 plus 0 and RAID 6 plus 0, which stripe data across multiple RAID 5 or RAID 6 volumes. Now that we've taken a look at how RAID protects data, it's also time to consider the limits of RAID. The first is high availability. RAID is meant only to protect the disk drives located within a server. If the server fails, RAID cannot protect us. It's not HA, and by itself it cannot fail over to another server. The second is RAID rebuild times. With increased drive capacity comes longer rebuilding times. As a result, the storage will run in a degraded mode for a long time, which can affect production workloads. Plus, the longer it takes to rebuild a disk, the more we are at risk of encountering another failing disk or a media failure. And the third is scalability. RAID cannot scale across multiple storage servers. When you need to store hundreds of petabytes of data, you will need lots of servers. To protect data stored at this scale, we'll use distributed replication or distributed erasure code.
Erasure coding is a form of encoding that works by splitting a unit of data, such as a file or object, into multiple fragments or data blocks. Then it creates additional fragments or parity blocks that can be used for data recovery. In the event of a failure, the parity fragments can be used to rebuild the data unit without experiencing data loss.
Erasure code, the original data can be reconstructed even when a large number of blocks disappear. Let's look at an example of erasure code with a set size of 12 and a parity of 4. Here we make 12 separate writes, 8 data writes, and then 4 parity writes. Any 4 drives can disappear or fail, and the original data can still be read and reconstructed. This advanced level of data protection costs us only 50% more storage. For example, to protect a 10 megabyte file, we will need to use 15 megabytes of disk space. We can also increase the level of availability by increasing the ratio of parity to data. Distributed erasure code improves on the previous example by writing across both servers and disks. For this example, we will use 12 servers, an erasure code set size of 12, and a parity of 6. Data is distributed evenly among the drives and the servers, writing first to one disk on each server, and then writing the next object to the second disk on each server, and so on with the next object. Now, with distributed erasure code, multiple random drives can fail, and entire servers can go offline, and yet we will continue to serve data. As long as we have 6 drives in our erasure code set, we can continue to read and reconstruct data. Consider that this high level of availability is accomplished with a low cost in storage consumption. In this example, an erasure code set with 6 data and 6 parity writes requires only 2x the storage. That is, a 6 megabyte file will consume 12 megabytes on disk. If you talk to an expert about erasure codes, they'll use terminology that can appear intimidating, but it's actually really simple. They use terms like symbols, N, K, and M. In the case of data storage, these symbols stand for erasure code set size, data, and parity. An erasure code set size of 12 with 8 data and 4 parity is represented as N equals 12, K equals 8, and M equals 4. For example, as 8 gigabytes of data is received, that 8 gigabytes of data is divided into 8 1 gigabyte data chunks. 4 1 gigabyte parity chunks are calculated using Reed-Solomon codes, and finally the data and parity chunks are written to storage devices in a random order. Most erasure code implementations let you choose the number of parity chunks to save with the data chunks. For example, an erasure code set size of 12 can use as little as a parity of 1 or as many as 6. With higher numbers of parity, we achieve higher levels of durability. And it is possible to use more than 2x parity, but that wouldn't increase the durability significantly, and it would waste capacity.
Data mirroring refers to the process of keeping a backup database server for a master database server. If, for some reason, the master database is down, the mirror database can be used as an alternative. Data replication, however, is the process by which data residing on a physical or virtual server or cloud instance is continuously replicated or copied to a secondary server or cloud instance. Organizations replicate data to support high availability, backup, and/or disaster recovery, depending on the location of the secondary instance. Data is either synchronously or asynchronously replicated. Data can also be spread across multiple geographic locations so that the user can download the file from the nearest location to avoid network delays and any slow response.
Replication is very easy to understand, but hard to implement correctly. Most importantly, we need a minimum replication factor of 3. That is, 3 copies of the data to guarantee data consistency. Why is this? Well, the only way to establish the validity of the data is by comparing the copies of the data with each other. If 2 copies of the data are identical, only then can we prove that we have a valid copy of the data. You cannot achieve this quorum when you have only 2 copies of the data. We can't prove which copy is valid. Having more than 3 copies can provide greater levels of consistency and data protection, but it also means taking a hit on write performance and usable capacity. It also takes more time to guarantee that all replica copies are identical. There are algorithms like Raft and Paxos that are used to achieve consistency with lots of nodes, and you can get a PhD in this topic alone. Distributed replication differs from the previous example by replicating data across a lot more servers. When you have many servers and use a replication factor of 3, you still make 3 copies, but write the data randomly to 3 different nodes. This is how distributed replication works. The code that chooses the nodes must be written in such a way that new data will be written to nodes in a completely random fashion. This increases data survivability and distributes the data evenly across all the servers. There are no limits to the amount of data that can be stored when using replication to protect the data. As you reach the limits of the existing storage deployment, simply add more servers and continue writing data. The replication method of data protection is employed by Hadoop HDFS and cloud storage providers specifically because it can scale without limits. RAID, on the other hand, is limited. As a data protection scheme, it can only scale to support the storage contained within a single server. Protecting data by making multiple replicas results in write amplification. A client that tries to write data has to wait for all the replicas to be completed, and this can result in slow write performance. There is a way to improve write performance. By writing the first copy and immediately acknowledging the client experiences great performance. Then we can complete the other writes in the background. This method of acknowledging writes and then replicating the data in the background is called eventual consistency. Unfortunately, if another client tries to read the replicated data before all the mirrored writes are done, there is a chance that it will get incomplete data or no data at all. So we can increase the write performance, but in turn, we're creating a data consistency issue. Thus, the use of replication requires careful consideration of the trade-off between performance and data consistency.
Hierarchical Storage Management, or HSM, provides an automatic way of managing and distributing data between the different storage layers in order to meet the user's needs for accessing data while minimizing the overall costs. The concept of HSM involves the placement of data items in such a way as to minimize its accessibility. The RMS provides an interface to utilize this feature.
Okay, before we begin on software design though, we need to talk about hardware, particularly storage media. And understand what the properties are of storage media, because they're going to have significant effect on the design of the software we're going to want to build. We want to write software that's going to make this storage media look fast. Now, there are major implications of the fact that we're dealing with disks. The most important one is in our programming model. We no longer have a model where we have objects in memory that we can dereference pointers on. Instead, we have an API to get things from the disk. We can read and we can write. And we read and write in units of a page of data, which is a fixed amount of data to and from disk to RAM. So we can read from disk to RAM, and we can write back from RAM to disk. And you can think of a page being like a 32 kilobyte object. So we're going to move these relatively small objects up and down from memory to disk. But we cannot address a particular bit on the disk. We cannot address a particular byte on the disk. In order to address anything on the disk, we have to bring its page into RAM, and then we address location in RAM to read or write the values on that page. Now, these API calls to read and write pages are very, very slow relative to CPU speeds. And so we're going to want to plan our reads and writes very carefully. And a lot of what we're going to do in database systems is to make sure that we're reading and writing to the disk exactly when and how we want. Now, this might seem like a drag, this idea that we have to do reads and writes, and we can't simply program with objects and pointers and references and all the things we're used to in our programming languages. But sometimes, particularly for data that we care about, having a very explicit API can be a good thing. So for example, if you've ever programmed in C or C++, you know that sometimes you can get a stray pointer and accidentally overwrite parts of memory that you didn't mean to overwrite. Similar things can happen in other programming languages as well. And we want to make sure that we don't mess up our stored data on the disk in the database. And so having to bundle that data up, put it in a page, and then push it down to the disk actually is a form of discipline that prevents certain kinds of errors that we get when we're writing programs. One way to think about it is this. You've probably written a lot of programs. Are they correct? Almost nobody's programs are perfectly correct. But the data that they read and write to the database can be checked more easily because it's going through this simple API. Now let's talk a little bit about the costs of disks and why it is that we might use magnetic disks in this day and age. This is data as of summer 2018, looking to spend about $1,000 at a typical online website. And so here's what you get for $1,000 worth of storage at Newegg, which is an online computer vendor. For a magnetic disk for $1,000, so a hard drive, if you look at sort of enterprise class hard drives, you can get about 40 terabytes for $1,000. If you want a much faster solid state disk, for that same $1,000, you only get 2.3 terabytes. So a factor of over 10, almost 20, a factor of 20 less storage for your money. And if you want to keep your data in RAM for $1,000, you can only get about 80 gigabytes of enterprise RAM. So that's many orders of magnitude less than what you get for magnetic disks. So in terms of storage density, hard drives are still a phenomenal bargain. And that's why they still get used in database systems for very large databases. Now, generally, we think of storage as being in a hierarchy. And if you've taken a computer architecture class, you may have seen a figure like this. Things at the top of the hierarchy are small and fast. So the extreme of that being the registers on your CPU. And then things at the bottom are big but slow. So magnetic disks are a good example of that. Now in database land, the database and the logs and backup information are typically stored on disks for very large databases, or even on what's called tertiary storage. So if disks are secondary storage and RAM is primary storage, tertiary storage might be something like a backup service in the cloud or a tape drive. All right, so that's where your database and backup logs are often stored for very big databases. Now, some databases, depending on the deployment, might store their database in a solid state disk if it fits. So a modest sized database, it might be worth it to pay more for storage because you get more speed and keep it on an SSD. This would be true, for example, for a database that fits on your laptop. Your laptop these days probably has an SSD, and it's going to be much faster than a magnetic disk. There are, for currently used data, for the data that's hot, we want it to be in RAM. And there are, in fact, databases that fit entirely in RAM. But for the most part in this class, we'll look at more scalable architectures where the database can be in secondary storage like SSD or disk. Now let's look at some numbers. These are fairly recent numbers. An L1 cache reference is about a half a nanosecond to perform. By contrast, go all the way to the bottom. To read a 1 megabyte from a magnetic disk takes something like 20 million nanoseconds. All right, so many orders of magnitude difference. And to give you a flavor of how different these things are, it helps to think about not time, but space. So here's an analogy from Jim Gray, who's a pioneer of relational databases and transactions, and winner of the Turing Award. And he makes the analogy with this. Registers are like your head. Okay, by contrast, going to disk is like going to Pluto. Right, that's the timescales we're talking about. If it takes a minute to get something out of your head, and it takes 2 years to get it from Pluto. Okay, so on-chip cache might be in the room, on-board cache in your building. Going to memory might be like going from San Francisco to Sacramento, which is where Jim Gray lived in San Francisco. So that's about a 1.5 hours drive. Going to disk is like going to Pluto. All right, and then of course going to some like cloud service, tape optical robot, whatever, that might be infinitely far away, like Andromeda Galaxy. Okay, so these are the orders of magnitude we're talking about. This gives you a sense of how bad it is to go to disk, or even in a computer, how slow it is to go to RAM. So the regime we're going to be focused on in database systems is that memory to disk boundary, which is the difference between 1.5 hours and 2 years.
So much for storage technologies at this part. Let's summarize what you've learned in this lesson. In this lesson, you learned what a storage array is, and then we looked at the key components of the storage array, and these are controller enclosure, drives and drive enclosure. Next, we looked at the enclosure addressing scheme, and then we looked at what a SCSI enclosure service processes. After looking at the components of the storage array, we saw how these components work together. We then saw the benefits of storage arrays. We also looked at what a direct attached storage or DAS is, and then we looked at the advantages of the storage array over the direct attached storage. Next, we looked at the types of storage arrays, and these were network-attached storage or NAS, a storage area network or SAN array, and unified array. Next, we looked at object storage. When we covered the NAS, we also touched upon the file-based protocols such as NFS and SMB and CIFS that are used by the NAS arrays to communicate with the host computers, and then we looked at what a storage network was. When we talked about the storage network, we touched on block-based protocol. Lastly, when we covered thus in array, we also looked at LANs and volumes. Next, we looked at the data protection ways and HSM. In the future, we will interpret and review other topics of storage and archiving, and we will refer to the function of each in the field of digital video and the video automation workflow. Media asset management is the process and software used to manage high-volume video and multimedia files. It originated within the film and broadcast industry to accommodate the need to manage large, rich media files. As a result, MAM became an essential part of the video production process, as it allows you to store and manage your rich media library from a centralized, reliable source. Since the advent of videotape, broadcasters and enterprise-class media organizations using audio, video, and rich media have employed media asset management systems to aid in the storage, cataloging, and retrieval of static and moving media assets. Those MAM systems have typically remained a comparatively separate function from the production, playout, and distribution sides of operations. More often than not, only individual tasks such as simple cataloging have been integrated into the many OEM systems that include some degree of MAM. Serving devices, such as video servers or library management systems, like Sony Broadcast's LMS product line, needed these features to manage the videotape or digital files contained on them. Given the uniqueness of these early requirements for MAM, the OEMs would typically write their own software and integrate it directly into their products. This practice changed once video server systems emerged. Broadcast television automation systems have also carried MAM components in their program and commercial playout platform, up to and including the current evolution of video servers. Newer digital broadcasting platforms that run on commercially type hardware would also manage these assets with their own flavor of MAM. Until recent times, with the proliferation of file-based workflows and the growing scale of storage systems, what has been missing in a MAM infrastructure is the ability to fully integrate media asset management across the entire production workflow, from planning to scheduling and acquisition, through broadcast release, packaging, distribution, and archiving. New dimensions in information technology now make it possible to gain a much richer degree of integration, one that marries media and management into a harmonious operating environment across the enterprise. This part will look at the fundamentals of media asset management as it applies to moving media platforms and digital storage systems utilized in the production, play-to-air, library, and archive processes. Exploring the topics related to managing media-centric assets, one finds there have been a number of similar terms applied to essentially a common category of topics. The terminologies have emerged from various segments of cataloging, searching, and retrieval-related activities, such as libraries, print-based publishing, and the web. Media asset management, content management systems, production asset management, digital asset management, and asset management systems, which generally include audio, video, and images. In other words, media asset management in a digital environment. We will touch upon the parallels found in web systems, but that topic is a much broader one that will not be addressed in depth. Let's turn to media assets and content. In most fundamental form, a media asset is a form of content. Content can be information that is found in unstructured, weakly structured, and highly structured forms. These forms of information, as media assets, are made available to users through the physical components of electronic storage, networking, and serving systems. These assets may be used by both humans and machine-based entities. Media assets consist of multimedia-based unstructured information objects such as pictures, diagrams, presentations, and other rich media such as those comprised of audio and video assets. Before information becomes an asset, it may be referred to as a media information object, a component that only presents information and that becomes more valuable when structured metadata are linked with that object. Once metadata are included, the media asset becomes more available, is searchable, able to be repackaged, and can be associated with databases that allow integration of the metadata records for secondary, extensible purposes. To sum up, media asset management is the process and software used to manage high-volume video and multimedia files. It originated within the film and broadcast industry to accommodate the need to manage large, rich media files. As a result, MAM became an essential part of the video production process as it allows you to store and manage your rich media library from a centralized, reliable source. I would like to draw your attention to define some of terms that are used in media asset management workflow, such as EDL, annotation, logging and cataloging, storing, retrieval. In computerized editing, an edit decision list or EDL is used in the post-production process of film editing and video editing. The list contains an ordered list of real and timecode data representing where each video clip can be obtained in order to conform the final cuts. EDLs are created by offline editing systems, or can be paper documents constructed by hand such as shot logging. These days, linear video editing systems have been superseded by non-linear editing systems, which can output EDLs electronically to allow auto-conform on an online editing system. The recreation of an edited program from the original sources, and the editing decisions in the EDL. They are also often used in the digital video editing world. So rather than referring to reels, they can refer to sequences of images stored on disk. Some formats, such as CMX3600, can represent simple editing decisions only. Final Cut Pro XML. The Advanced Authoring Format or AAF and AVI synth scripts are relatively advanced file formats that can contain sophisticated EDLs. Video annotation is a labeling process used to AI to detect objects and audio in videos. Autonomous vehicles are a notable use case of video annotation. They rely on sensor and camera capture video data that's then labeled with cars, pedestrians, traffic signs and other objects to train the car where it needs to go, how to react to its environments and what to avoid. Historically, video annotators had to synchronize data and tracked objects between frames manually. Today, AI-powered tools are available to help automate tagging and make the annotation process more efficient. Video is a more complex data structure with motion, audio, and image baked in, yet it allows teams building AI to access more information on objects and their environment. In many cases, companies have found that video can provide greater output for machine learning models than images without adding costs. To unlock the benefits of video annotation at scale, teams need to partner with data and technology provider. Video logging and catalog is the process of building records that go into our videos. And the reason we have those records is so that people can find our materials more easily through the catalog by searching for them, and we have a way of organizing those materials. Video Cataloger is a software that's gonna help you quickly find the videos you are looking for, so it's not hard to use a few pointers to get started in the right way, or according to me the right way. So let's get started. So the first thing, what is a catalog? It's basically a database file pointing to videos you have in your collection, and it contains all the metadata about the video files. So because of this, we probably want this catalog file in a location on your storage system is quick to access, since normally when you use the program, when you search, it's only this catalog file that it's touched. It normally never touch videos files unless you're actually watching a video or if you're adding new videos to your video catalog. The process of digitally storing moving images and sound begins by converting one's analog video and audio signals into a stream of discrete representations of binary numbers corresponding to sampled levels of chroma and luminance, or for audio, correlating the changes in dynamic air pressure, which have already been converted into electrical signals as they were captured by transducers over time. In the digital media world, this string of binary information is represented as data and is often referred to as bits and bytes. Storing and retrieving is a two-part process which involves the storage of data on some kind of storage medium so it can be preserved and then later retrieved for use by another process at a later time. Typically, when data is stored, the method of data representation changes. For example, data from the computer in electrical form is stored onto the hard disk in magnetic form. This is also true for retrieving, as data may be converted back from magnetic data into electrical signals for use by the computer. When data is processed by the processor, the processed data needs to be taken out of the processor before any other data can be processed. This involves storing this data on the computer's primary, for example RAM, or secondary, for example hard disk storage mediums. Once the processor is freed up, the processor can retrieve and process another portion of data from storage. Historically, MAM systems have focused more on providing storage management and were not involved with workflow or operations. The MAM would be that instrument that connected the files on a storage platform with a database-driven application that looked up certain tags, information provided by the user at the time the media was ingested to the storage system. The simple MAM allowed for the rudimentary searching of the media based upon that user-generated information. The extremely simplistic approach was at best the electronic equivalent of a label placed on a videotape cassette or the 3x5 card stuck in the container that housed that tape. Two of the more traditional approaches to MAM implementation employed early on were in tape-based systems and digital video server systems. MAM solutions for videotape typically involve media assets stored in a robotic library with supporting information about those tapes kept in a data library housed on a dedicated computer system. Software cataloged the library based upon the tags records that were entered into that application by the user. Usually at the time of ingesting the material into the tape library, solutions like these have been around since the mid-1980s. At the most basic level, at least for broadcast applications, the library catalog data would contain a house number that was paired against the information contained in the broadcast traffic system that described that asset. This house number was the database key link between what was in the videotape library's database and what was contained in the traffic system's database. Traffic systems held the contractual information about the content, but had no network or other connection to the robotic library. It essentially knew nothing about what actually resided on the physical tape media. In the early days prior to automated or robotic tape-based play-to-air systems, see the workflow example in slide figure. The tapes or films on the broadcast library shelf would be manually collected according to instructions from the traffic department, moved to the dubbing transfer area where an operator would load the tape or film and cue it, then either electronically dub each tape to a master commercial reel or ready videotape transports or film projectors for playback by an operator or other triggering mechanism associated with the station's master control play-to-air operations. Once automated tape-based play-to-air libraries were put into use by broadcasters, an operator would load the tapes into the play-to-air robotic library and enable applications that were built into this robotic systems control system referred to as a library management system or LMS, which would be triggered by the station's external automation interfaces at the appropriate point in time based upon the station's program schedule. This was essentially the entire sum and substance of the media asset management process prior to the era of video servers. Drawbacks to tape-based systems. I'd like to expand on a problem. The principal drawbacks to this type of MAM was that there was no integration or interaction between the asset management, in general, and operations. Tape was a one-function, one-action at a time instrument of physical media. Tape offered no collaboration. That is, when a tape is in use, no one else could have access to that material except as linear video on a routable video transport system. Work would be limited to just one individual, working on one specific task and only with that specific tape. To use that asset for any other task, play-to-air, editing, or copying, a person would have to physically retrieve the tape from a shelf or library, take that tape to a location with equipment capable of playing that tape, load the tape, and then play the tape. No integration between the media asset management system and the playout equipment was possible, because assets were stored on tape in the metadata box. Those assets would be stored separately in a computer. Users could perform searches on that metadata, but the physical retrieval process would be manual. It would take considerable time to locate and transport the assets, resulting in a risk that those assets could be lost or unavailable because they were already being used by others. The simplest functions of browsing could be quite time-consuming, requiring handling the physical asset, usually in its original form. Physical media is subject to use degradation each time the tape is played or handled. When the asset was stored on analog videotape, duplications would always be of poorer quality than the original. Even with digital videotape, the cloning process would have to be manually managed, had to occur in real time, and should any updates to the metadata be necessary, the accuracy of that update could be compromised by the user improperly recording that updated information or forgetting to make the update altogether. Seldom would these systems account for usage counts or changes in media quality. All of these disadvantages would directly translate into poor productivity. Mistakes would occur due to inefficient collaboration, introducing significant delays into the production and broadcast processes. The introduction of video servers as a buffer between tape-based libraries and play-to-air operations helped alleviate a portion of the manual processes of asset management, but not many of them. With a video server implementation, each videotape would be physically transferred from the tape media to the digital storage platform, where certain data about the asset would be entered and communicated to a basic media asset management program resident on the video server. If the transfer was part of the broadcast station's play-to-air automation, that information was collected in that platform as well as the automation program, due to the proprietary nature of each of these variant platforms. The information on one system was seldom replicated in its entirety on another. Certain systems needed certain information while other systems might need that same information or would require a different set of data. Video servers with their associated storage platforms would maintain their own database correlated with information that the user would enter during the ingest process. Such information, or metadata, would basically instruct the video server on where to begin the playout through metadata called the start of message on, and when to stop the playout of that media, which in turn would trigger the next clip in a sequence of files to be played back during a commercial station break. This later metadata element, called the end of message, would set the point here playout of active video would cease. The EOM would sometimes trigger the next song to roll if the clip was not the last event in the sequence of a station break. Other video server specific information would be more structural in nature, such as the location of the clip on the actual hard disk or storage platform, the codec, the time vocoder frame, count of the clip, the number of audio channels, and other technical information. The video server's internal database would be application specific to that video server. The video server would tie the data to a clip identification number, which the video server would associate with an external database contained on the station play-to-air automation system, or, if the playout program was self-contained on the video server, with its resident application. For the most part, the video server's storage, search, and retrieval functions had several disadvantages stemming from the fact that there was no integration between asset management and operations. Any outside interaction would be contained to the station automation system, or depending upon the video server, possibly a simple clip playback program resident to the video server. Lack of media asset integration. Digital storage systems might include toolsets integrated into nonlinear editors or the traffic or scheduling programs, or as a part of the media ingest or acquisition applications that provided some level of MAM. When these toolsets were integrated with the storage platform, they could offer the advantage of having immediate access to those media assets contained on that specific storage platform. These tools would usually be incompatible with other platforms and would be unable to access them without special customization for the MAM. Metadata that was entered into one system would only reside within that system and would not be capable of exchange throughout the MAM. This interoperability issue leaves each of the systems isolated from one another, requiring users to open specific applications on each platform that would be unable to be cross-linked into the principal MAM system. As DAM has grown over the years to be able to better support rich media files, the gap between MAM and DAM has narrowed. Originally, DAM functioned as a photo, graphics, and file library before it evolved to support rich media assets and the video production process. Today, MAM and DAM are often confused as they're both solutions used to store, manage, and access digital assets. In addition, they both streamline the content creation and distribution processes. They both make it easy to use assets and track that usage with analytics. And they both ensure safe, long-term storage of large files. The distinction lies in the two systems' intended use. Since MAM was created to support the video production process, its functionality tends to best serve industries working primarily within rich media content management workflows. But as today's video production process often involves more than just video and audio files, media teams are increasingly opting for evolved DAM systems over more specialized MAM tools. When a document, image, or other type of data are created, certain parameters should be added with the item as part of the complete file. Such elements, otherwise called attributes, include items such as a file name, the size or type of file, the date it was edited, etc. These metadata are called structural and generally will not change. For picture-based assets, the image may include metadata describing the pixel dimensions, how large the picture, the color depth, for example 24-bit, the image resolution, for example 300 pixels per inch, when the image was created, and other data. A text-based asset would likely include metadata containing information about the number of words or characters in the document, who the author is, when the document was created, and potentially a short summary of the document. Web pages often include metadata in the form of meta tags. Description and keyword meta tags are commonly used to describe the web page's content, which enables third-party search engines to use this metadata when adding those web pages to their search index. This metalanguage or metadata aid in speeding up searches, allow for the creation of catalogs, can be created automatically by the encoding platform, and can be added to by the user, author, or owner. Metadata in a digital media environment are used to manage the file system information. They describe, at their highest level of importance, where the files are kept so that other subsystems may search for them, retrieve them, update or process them, and the like. There are two general categories of metadata for media systems, called structural metadata and descriptive metadata. The example of figure shows a typical set of metadata screenshots where users or machines enter or display the respective forms of metadata fields. These are the data used to describe the physical attributes of a file. For video assets or video essence, they will include such information as the format of the video file, their bitrate, the resolution, and the container, for example wrapper type, the overall media asset management system, and its peripheral components, depends upon the integrity of the structural metadata associated with each independent file. It is for this reason that users should never forcefully change the attributes or tags in this important set of data. The result of modifying structural metadata would be the disastrous equivalent of changing the file extension on a computer file. In a more global sense, structural metadata are as important to the MAM as the file allocation table or FAT is to the hard disk drive. The Society of Motion Picture and Television Engineers has standardized the structural metadata of the MXF file format as SM380 Portuguese escudos M, which contains the technical parameters of the stored material, defines how the material is played out, and provides a plug-in mechanism for a descriptive metadata scheme. This information may be generated either by the system or by the operator. User descriptive metadata examples include shot logging, track naming, availability, allowed dates of usage, and rights or permissions. Depending upon the organization, descriptive metadata may vary: simple -10, 20 fixed terms, or very complex hundreds of elements or fields. Descriptive metadata may be very selective so as to limit the number of variances that a user might enter. For example, in a baseball game, some of these entries might be limited to the number of possible play combinations, the number of batters, the players' names, and what occurred with each batter at the plate: strikeout, walk, fouled out, run, hit, error. These incidents may be logged using a specific application that is constructed from a tool set by the user or administrator. It is important tagging information that supports search and retrieval of media from the MAM system. SMPTE, as part of their standards and practices documents, provides a recommended practices of this writing version RP 210.11.2008 that includes the framework for a deep set of terminologies contained in a user-addressable online instrument built on a node and leaf structure. The SMPTE Data Element Dictionary, formerly called the Metadata Dictionary, is a data element register that defines data elements, including their names, descriptions, and identifiers, for association with essence or other metadata. A full explanation is contained in SM335 Portuguese escudos M. The spreadsheet form details can be found at www.smtra.org divided by under the file RP 210.11 XLS. One can see the depth that such metadata can take, as it begins at the administrative levels and goes well beyond the coding levels for media-related files and essence descriptions. Interoperability. Interoperability is a key component of any metadata strategy. Elaborate systems that are independently devised for only one archival repository will be a recipe for low productivity and high costs, and will have minimal impacts. Richard Gabriel's maxim "worse is better," which originated from when he was comparing two programming languages, one elegant but complex, the other awkward but simple, correctly predicted that the simpler language would spread faster, and thus more people would come to care about improving the simple language than otherwise improving the complex one. Gabriel's prediction was found to be correct, as is demonstrated by the widespread adoption and success of Dublin Core, which was initially regarded as an unlikely solution by the professionals on account of its rigorous simplicity. now one of the more recognized initiatives related to metadata. This work dates back to 2000 when, at that time, the Dublin core community focused on application profiles as a type of metadata schema. Application profiles, as schemas, consist of data elements that are drawn from one or more namespaces, combined together by implementers, and then optimized for a particular local application. In the application profile concept, metadata records would use Dublin core together with other specialized vocabularies to meet particular implementation requirements. The motivation for the work on the Dublin core was to develop a set of 15 simple data elements that could be used to describe document-like networked information objects in support of discovery activities. Dublin core data elements consist of the following: title, creator-author, subject and keywords, description, publisher, other contributor, date, resource type, format, resource identifier, source, language, relation, coverage, and rights management. The Dublin core achieved wide dissemination as part of the Open Archives Initiative Protocol for Metadata Harvesting OAIPMH and was ratified as IETF RFC 5013, NSI, and ISO standard Z3985-2007, and ISO standard 15836, 2009. Since 1997, the Dublin core data model has evolved alongside the World Wide Web Consortium's www.w3c.org work on a generic data model for metadata, known as the Resource Description Framework RDF. As part of an extended set of 1401 metadata terms, Dublin core ultimately became one of most popular vocabularies for use with RDF, most recently in the context of the linked data movements. Developed by the Public Broadcasting Service (PBS) with development funding from the Corporation for Public Broadcasting (CPB. The project, which was initially published in 2005, provides a common set of terms and capabilities that address metadata and associated media asset management activities for use specifically by many public broadcasting stations, organizations, and information systems. These entities use this 48-element core document to describe the intellectual content, property rights, and instantiations, formats of their media items. The PB Core project has been finalizing its XML schema definition. XSD is the main framework upon which all the PB Core elements, their relationships, vocabulary pick lists, and data types are organized and defined. PBS is building an accurate and meticulous XSD to ensure that when PB Core compliant metadata descriptions are shared between data systems, the contributing system and the receiving system are both able to machine read and faultlessly interpret and display these descriptions. Formerly known as the Public Broadcasting Metadata Dictionary Project, PB Core is designed to provide, for television, radio, and web activities, a standard way of describing and using this data, allowing content to be more easily retrieved and shared among colleagues, software systems, institutions, community and production partners, private citizens, and educators. PB Core can also be used as a guide for the onset of an archival or asset management process at an individual broadcast station or institution. PBS sees this as a standard pivotal to applying the power of digital technology to meet the mission of public broadcasting. In the process of creating the PB Core XSD, they determined enhancements to the underlying structure of PB Core were necessary. These enhancements aid in the binding together of related metadata elements, for example title and title type, into new element containers. The original 48 PB Core elements are now becoming a more structured hierarchical model consisting of 53 elements arranged in 15 containers and 3 subcontainers, all organized under 4 content classes. Usage metadata is yet another form of descriptive metadata, typically a subset of descriptive metadata. Usage metadata describes life cycle information about a video clip or file, such as when the camcorder actually first captured the contents, depending upon how the metadata schema is implemented. This might include the time of day, the shooter if the camcorder logs that information, and the MAC address of the recording equipment or the name associated with the physical recording media. Schemas, defined basically as a protocol that describes how one collects all these data sets together. Schemas have different meanings depending upon the systems they are associated with. For example, in computer science, an XML extensible markup language schema is a way to define the structure, content, and, to some extent, The semantics of XML documents, since XML is becoming the de facto standard of writing code for media asset systems, particularly one that is human understandable. Many of the metadata systems are being written or translated into XML. Standards, practices, and policies for metadata. Much of the work published on metadata, in general, comes out of the professional librarian space. Setting policies that cover the endless possibilities for metadata applications is beyond comprehension, but there are still several efforts as previously described that continue in that domain. Diane Hillman's Cornell University infamous statement, "There are no metadata police." Elevated awareness of standards, practices, and policies. There are indeed prescribed standards and practices that can be observed and followed when designing a usable and extensible metadata platform. Some of these have emerged from the work in MPEG 7 and in various other global activities by standards committees and their study groups. It would be nearly impossible to present all of these, but the further reading section at the conclusion of this chapter will provide some links to current and previous activities. Storing metadata. There are two principal philosophies associated with where metadata are stored for media-centric applications. One belief is to associate metadata to the file in an external database housed on a separate server platform. The alternative is to embed the metadata with the actual file. Both have their pros and cons. Metadata, particularly descriptive metadata, are quite dynamic. The size of the metadata file, that is, the byte count of the XML-based information, continues to grow as the file content moves through the production, distribution, and archiving processes. It is for this reason, and the risks associated with the loss of the metadata embedded in a file, that many MAM systems will employ a discrete server platform that isolates the actual essence of the file from the descriptive metadata. Structural metadata are almost always carried with the file itself. These metadata do not necessarily follow XML formats, as structural metadata are most useful to devices, such as decoders and video servers, when the file is first presented to the playback system of root-level server platforms. Descriptive metadata would not necessarily be carried or contained wrapped within the essence portions of a media file. Given the dynamic nature of descriptive metadata during production and other workflows, this would potentially require that a new version of each file would be created every time that a new element is added to the metadata. This would require a continual growth in storage systems for what would be highly duplicative information. Organizations like the Advanced Media Workflow Association (AMWA) are working on schemas that can link the metadata with the essence elements through versioning methods. It is beyond the scope of this book to delve into this topic, but expect to see continued adoption of these methods through the advancements in the MXF standards and practices. So much for MAM and metadata at this part. Let's summarize what you've learned in this session. In this lesson, you learned what is MAM, and then we looked at type of media content, metadata, MAM and DAM, and how MAM components work together. I'd now like to move on to the next part and talk about studio automation and playouts.